students, and welcome to the new episode, which is directed to the both of AS and A-level candidates. In this episode, I'm going to solve three different questions, which are covering the bonding and structure topic questions. These questions are cited from different papers of the same year, 2017, but from different series, March, June, and June. So let's start with the first question. Question number 2 is about hydrogen halides. Hydrogen halides are compounds formed when halogens from group number 17 or 7 react with hydrogen. The bond polarity of the hydrogen halides decreases from the HF to HI. That means across the group, down the group, the polarity, it will be decreased. Here in the table, some relevant data are shown in the table. Hydrogen halides, HF, HCl, HBr, and HI, and their boiling point, and HX bond energy, which is measured by kilojoule per mole. In the first question, explain the meaning of the team bond polarity. Bond polarity, you can define it, the bond which is formed between two, or you can say, yes, two different partially charged atoms. That means the bond which is formed between two atoms. These atoms, they have different partially charged. For example, we can say HF. This bond between the hydrogen and the fluorine atoms is bond polarity or polar bond. Why? Because this bond is formed between two different atoms. Their partially charge is different. This one partially negative and this one partially positive. In the next question, suggest why the boiling point of hydrogen fluoride is much higher than the boiling point of the other hydrogen halides. Now, because the fluorine has very high electronegativity, actually is the most electronegative atom in the periodic table, the physical bond between the hydrogen fluoride molecules is very strong, which is hydrogen bond. While in the other hydrogen halides, the physical bond between their molecules are weaker than which is in the hydrogen fluoride. So here you need to talk about what's the type of the bond. Here we have hydrogen bond. Hydrogen bond in HF. But in, actually not in, between. You have to say between HF molecules, hydrogen bond between the hydrogen fluoride molecules, but between the other HX van der Waals. Force, which is weaker than the hydrogen bond. Okay. The second reason, because here you have two marks, so the second reason, the amount of energy which is required to break the hydrogen bond more than the amount of energy which is required to break the van der Waals forces between the other HX. So you need to talk about how to break this bond, the amount of energy, and the type of the hydrogen, the physical bond. So we can see here in the table the boiling point and melting point. The boiling point of HF is very high if you will compare it with the others. Okay. Describe and explain. Here you have to describe and explain the relative thermal stability of the hydrogen halides. So first of all, let's describe it. How is it the thermal stability from the bond energy? That means these molecules, they will be resistant to the high temperature or not, or which one it will be resistant higher than the other. So we can see here in the HF, the bond energy is 562 watt, while in the HI it's 299. So we can describe it, the bond energy or the thermal stability decreases down the group. Why? Why? That means you need to talk about two reasons. One mark here and two mark for two reasons. Why? The size of the halogens, it's an increase as you go down here. So this, you need to talk about the size of the halogen or the number of level energies or the shielding, so or the atomic radius always is increasing as you go down across the group. So here, size of halide increase this down the group. Okay. The second reason, the bond energy decrease down the group. Okay, so these reasons they are explaining why the thermal stability of hydrogen halides are different. So the one with a small halide will have higher bond energy, so that means it will be more stable, thermal stability I mean. Okay. Another question, the equation for the preparation of hydrogen chloride using concentrated sulfuric acid is shown here. We have plus NaCl. This one we will form sodium hydrogen sulfate and hydrogen chloride. According to the Bronsted-Lowry theory of acid and bases, we will use this theory to identify the base and its conjugated acid in this reaction. Explain your answer. You need to explain the answer. So Bronsted-Lowry base, the one who will accept the hydrogen. So we can see in the sodium chloride, the Cl will accept a hydrogen and it's converted into HCl. So the Bronsted-Lowry base, NaCl, to be more specific, chloride ion. The chloride ion is the base. Okay, and the conjugated acid, this one, conjugated acid, you can say HCl. Conjugated acid, it's HCl. because acid and base. Okay, so the explanation why chloride we consider it as a base, because this one is acceptor of hydrogen plus, and the HCl, why it's acid, because it's donator of H plus. According to the Bronsted-Lowry theory, the one who will donate the hydrogen plus, it's the acid, and the one who will accept this H plus will be considered as base. Explain why the reaction of concentrated sulfuric acid and sodium iodide is not suitable for the preparation of hydrogen iodide. Here, if you will come back to your course book for the reactions of the halide salts, for example, sodium chloride, sodium bromide, sodium iodide with the sulfuric acid, you will see only with sulfuric acid you can form sodium chloride. But if you will react sulfuric acid with, for example, sodium bromide or sodium iodide, you will not have only the sodium bromide or the sodium iodide. Why? Because sulfuric acid, H2SO4, is very strong oxidizing agent. Okay, and if you will react the reaction, that means sulfuric acid with sodium iodide, you will not form hydrogen iodide only, you will form also iodine. Okay, you will form also the iodine. So actually you need only hydrogen iodide, but in the same time you will produce iodine. So this this reaction, it's not suitable to prepare preparation of hydrogen iodide. But this reaction only could be good method to prepare the hydrogen chloride. Okay, but with other hydrogen, if you need to prepare other hydrogen halides, this reaction, it's not good method, or it's not suitable for preparation of the other halides hydrogen. Here in this reaction, you have to calculate the hydrogen chloride undergoes a reversible reaction with oxygen. According to this reaction, the reaction is carried out at 400 Celsius in the presence of copper chloride catalyst. Use the data in the table to calculate the overall enthalpy change of reaction. Here you can see you have two enthalpy change of formation. Here you have kilojoule, okay, per mole for only HCl and H2O. We don't have formation of oxygen, you don't have formation of chlorine. Why? Because both of these molecules are not compounds. They are already oxygen, so we cannot form oxygen from it's already its element. Chlorine and oxygen already they are elements, and formation that means formation a compound from its element. But here oxygen and chlorine already they are elements, so we don't have enthalpy change of formation for them, so we will neglect both of them. So now you have to ask yourself, these are formation should be in the product side, but HCl, it's located where? In the reactant. So you will take this value negative, it will be positive 92, and time the number of mole, which is 4, plus then H2O, where is it? In the product side, that means it's formed. So you will take the delta HF of H2O without changing anything with the value. So it's negative 242 times the number of mole, which is 2, and this one it will give us this value, which is minus 116 kilojoule per mole. So this reaction is very clear. It's exothermic reaction. So this value, it will be written here. Again here, kilojoule per mole. State the type of catalyst used in this reaction. The catalyst here we have used it, copper chloride. Copper chloride, it's ionic compound, so it's clear. That means it's a solid. But you can see all the reactant and the products in the reaction, they are gases. So the type of this catalyst, it's heterogeneous, because the reactant and products are different from the state of the catalyst. So heterogeneous catalyst. Okay. Explain how a catalyst is able to increase the rate of chemical reaction by lowering the activation energy. Okay, so that means activation energy, sorry, you can here, if you have this reaction, this is the normal one, okay, but in the presence of catalyst, the activation energy, it will be lower, this one, okay. So in the presence of the catalyst, only you will lower the activation energy, so the rate of reaction, it will be increased. The reaction exists in dynamic equilibrium. The reaction was repeated at 1000 Celsius and the same pressure. State and explain the effect on the composition of the equilibrium mixture of the change in temperature. Here actually you need the reaction from the value, it's negative. Okay, if it's negative, that means your reaction is exothermic. So this one, it's negative 116. So if you will increase the temperature, already this reaction is exothermic. So this reaction doesn't need to increase its temperature. That means here it's 400, it's the optimum temperature for this reaction. But if you will increase the temperature, the reaction, it will be shifted to the left. That means your reaction, it will be shifted to the left. In this case, the yield of chlorine and H2O, it will be decreased. So we can say here, the reaction is exothermic, 1. And 2, you have to say increasing the temperature, the reaction will be shifted to the left. So both of chlorine and H2O will be decreased. According to the chemical reaction, the equilibrium reaction, your reaction, it will be shifted to the left. That means the reverse reaction. So that means the chlorine and H2O, they will be consumed to be converted into HCl and oxygen. In this equation, when 1.6 mole of hydrogen chloride are mixed in a sealed container with this 0.5 mole of oxygen and this temperature, okay, 0.6 mole of chlorine and 0.6 mole of H2O are formed. The total pressure inside the container is this one. Let's write the equation first of all. HCl plus oxygen Cl2 H2O 4 2 2. This is the balanced chemical equation. Okay, you started with 1.6 and this 1.5. So before starting the reaction you don't have chlorine and H2O. Okay, container with it at 400.6. So at 400 of oxygen at 400 Celsius, 0.6 of chlorine and 0.6 mole of H2O are formed. So that means 1.6 minus, you have 4x, and 0.5 minus x, and here you have 2x, and you have here 2x. How many mole of chlorine is formed? 0.6. 0.6. Okay, so what's the number of mole of HCl and oxygen are left? So from this thing here, 2x equal 0.6. 2x equal 0.6. So x equal 0.3. Okay, so what's the remain of this one? 0.5 minus 0.3, that means here you have 0.2. And 0.6 minus 4, 0.3, that means 0.6 minus, it will be 4 times 0.3, 1.2. So this one, it will give us 0.4. Here it's 0.4. Okay, so at the equilibrium you have 0.4 of HCl, 0.2 of oxygen, 0.6 of chlorine, and 0.6 again of H2O. So here is asking about HCl and oxygen. So HCl we said it's 0.4 mole and oxygen it's 0.2. Calculate the mole fraction of Cl2 and hence the partial pressure of Cl2 in the equilibrium mixture. Okay, so mole fraction of chlorine. Mole fraction of chlorine equal what? What do you have? How many mole of chlorine? You have 0.6 over, that means this part over all of them, because all of them are mixed in a one container. So here you have 0.6 plus 0.6, 1.2, 1.4 over 1.8, and this one it will give us 0.6 over 0.8. What's the result? Just let me check it, please. .6 over 1.8. Three. Okay, and the partial pressure of chlorine equal mole fraction time total pressure. Mole fraction 0.33 time partial pressure, it's total pressure, it's given here 1.5, this one power 5. So mole fraction is given here, and PCl2 here. Just you need to multiply these numbers together, and you will get the result. So just let me calculate it. So the partial pressure, it's equal 5 times power 5 Pascal, and this 1.333. Here, in a separate experiment, an equilibrium reaction mixture was found to contain the 4 gases at the partial pressures shown in the table. Here everything it's explained. Just use this information and expression given for Kp to calculate the value for Kp. Here Kp equal the partial pressure of chlorine, should be squared according to the balanced chemical equation, because balanced chemical equation, it's we have 4HCl plus O2, 2Cl2, 2H2O, and all of them in the gas. So this one here, it's it's already given here. Just you need to square this number time square the partial pressure of H2, and for HCl you have to it's a power 4, and this one. So at the end you will have the Kp, it's 1.05 times minus 5, and the unit here, this one, it will be cancelled with this one, because power 4, it will be with power 4, it will be cancelled, and this one is Pascal, so it will be Pascal minus 1. Okay, and the reaction is repeated without catalyst. State the effect on this on the Kp. Actually, Kp wouldn't change, because Kp is actually from its constant, so it will not be changed. Always you will have same ratio of the reaction. That means same ratio of different the number of moles of the reactant and product. So always Kp, it's constant. Okay, so if you repeat this reaction with catalyst or without catalyst, or with catalyst better than the previous one, the Kp is constant, but the rate of reaction, it will be affected. Okay, the next reaction question, nitrogen gas N2 is very unreactive. Explain why nitrogen gas is so unreactive. Nitrogen, there is a triple bond between the nitrogen atoms, so it's not easy to break all these three bonds, and this is first reason. The second reason, they are non-polar molecule. So because it's non-polar and a triple bond, is considered as a reactive molecule. Despite the low reactivity of nitrogen, oxides of nitrogen occur in the atmosphere through both natural and man-made processes. The natural one, when there is thunder lightning, that means there is very high voltage. This high voltage will make a reaction between the nitrogen and oxygen. They will react together to form nitrogen oxides, okay, or oxides of nitrogen, because different oxides of nitrogen we have. And also man-made processes, that means if we are going to increase the temperature to very high, temperature, very high temperature. So here in the question I explain why oxides of nitrogen can be produced by internal combustion engines. That means inside the engine of car, during the combustion of fuel, we need oxygen. This oxygen we will take it from the atmosphere, but with the oxygen will come the nitrogen. Okay, and oxygen, both of them are component of the atmosphere, so at once we will form nitrogen oxides. Okay, nitrogen oxide. Why? Because there is heat inside the engine. Heat, that means high temperature. State and explain, using a suitable equation, how oxides of nitrogen produced by internal combustion engines can be prevented from reaching the atmosphere. So in this case, what do we need? In this case, you need a catalyst actually. This is called catalytic converter. So here you need catalytic converter. Okay, so if you will use the catalytic converter and in the presence of platinum, because catalytic converter they are using platinum, you will have this reaction between nitrogen monoxide or dioxide, but here we will consider the nitrogen monoxide plus carbon monoxide. In the presence of the catalytic converter, you will form carbon dioxide and nitrogen. So just let's balance this equation. Here you have 2 and 4 with 2, so 2 here. Okay, so in the presence of catalytic converter, you will react the oxide of nitrogen, which is formed. They will react it with carbon monoxide, so you will convert both of them into carbon dioxide and nitrogen. Then you will evolve them to the you will let them to reach the atmosphere. And the next question is, state the role of nitrogen dioxide in the formation of acid rain by oxides of sulfur. So here the nitrogen actually let's write the equation, then we will see. Here the nitrogen dioxide, when we react with oxides of sulfur, for example SO2, you will form what? You will form nitrogen monoxide, okay, plus sulfur trioxide. Okay, the state here it's gas, 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 and gas. Then this SO3, which is gas, when it will react with H2O, because rain, you will form H2SO4. Okay, so in this case you have formed aqueous acidic rain. Now the question, what's the rule of nitrogen dioxide? The rule of nitrogen dioxide, it's catalyst. Why? Because to convert the SO2 to SO3, we need to make the reaction with oxygen in the presence of vanadium oxide, and this reaction, it needs this vanadium oxide catalyst. But here, if you have nitrogen dioxide, you don't need to have the vanadium oxide. Why? Because already the nitrogen dioxide, it's a catalyst. How is the catalyst? What's the type of this catalyst? It will be homogeneous, homo. Why? Because homo, that means the state of the catalyst, the state of matter of the catalyst, or the phase of the catalyst and the reactants, if they are in this from the same state, so it will be homogeneous. Okay, so suggest an equation to show that nitrogen dioxide can be contribute to acid rain. So NO2 with H2O, you will form HNO2 and HNO3. Both of them are acids. So let's balance the equations. Here you have 2 mole of HNO2, sorry, of NO2. So you will form these two acids. This is nitrous acid and nitric acid. Both of them are a solution, so, and both of them are a source of acidic rains. Now, explain how the uncontrolled use of nitrate fertilizers on land can lead to a severe reduction in water quality in rivers. Summarize these steps for explain how the uncontrolled use of nitrate fertilizer question. So here in the first step, you need to say fertilizer dissolved in water. Okay, so when the fertilizer dissolved in water, the growth rate of a plant will increase. Okay, so when the plants, they will increase, that means they will be very tall, and the river, it will be full with the plants, so they will prevent the sunlight to pass through the water. So the plants which are their roots in the water, they will not be able to do the photosynthesis. So without photosynthesis, that means the plants, they will die. So when they will die, there is, you know, the biodegradation. Biodegradation, it needs a bacteria, and there is a bacteria in the river, and also we need oxygen. So the oxygen, it will be consumed from the oxygen which is dissolved in the water. So by the end, the level or the concentration of the oxygen, it will be decreased. So here, look to the effect of fertilizers on the reduction of water quality in the rivers. That means water quality, that means the amount of oxygen which is dissolved in a water. That means if there is a water without good enough concentration of oxygen, the quality, it will be very bad, and it's not suitable for marines and also the plants. In the question 2, you have structure and bonding can be used to explain many of the properties of substances. You have copper, ice, silicon oxide, iodine, and sodium chloride are all crystalline solids. We have to complete this table. The name of type of bonding found in each crystalline solid, the type of lattice structure for each crystalline solid. So copper, it's metallic. Okay, metallic. And the type of lattice, it's metallic also. Okay, but how is it? It's a giant, we can call it a giant metallic. Okay. Okay. The ice, actually H2O. H2O, what do you have? You have covalent and hydrogen bond. Covalent between the hydrogen and the oxygen atoms, and the hydrogen bond between the H2O molecules. Lattice structure, it's you can say simple molecular, simple covalent molecule. Silicon oxide, it's here also covalent, here also covalent, but how is the structure? It's giant covalent molecule. Iodine, it's also covalent, but it's simple. Okay, simple molecular. And sodium chloride, it's ionic. And how is it? It's giant ionic. Okay. Name the strongest type of intermolecular force in ice. It's hydrogen bond. Hydrogen bonding. Draw a fully labeled diagram of two water molecules in ice showing the force in I, that means this question, and how it forms. So this is H2O, partially positive, partially negative, and with two pair of electrons, partially positive. Then you need to draw another molecule of H2O, partially positive, and here. So the intermolecular forces between the H2O, it's hydrogen bond. Okay, so this one, hydrogen bonding. Okay, how is it formed? It's formed between the partial positive hydrogen, which is connected covalently with very electronegative atom, which is oxygen, and with oxygen, which is also, we can consider this very electronegative atom, which is belong to the another molecule. Okay, and always the angle between this bond and this one and this one should be 180. Okay, here we have the graph represents how the temperature of a sample of copper, the melting point 1085 Celsius, changes as it's gradually cooled. That means here we will decrease the temperature from 1200 till it will be cooled down. So we will start from 1200. That is more than what? The melting point. So here it's liquid, then it's decreased, and here it's solidified because here the T1, this one T1, it's 1085. Okay, the melting point. Then when it's solidified, it's cooled down more, and here it's become fully solid. Identify the state of matter present during each stage of the process shown in the graph. So X, it's liquid. Y, here we said it's solidifying. That means here you can say liquid and solid. Okay, not all the liquids are converted into solid. Okay, it's a critical point, the melting point. Okay, and Z, it's fully solid because less than the melting point. State what's happening to the energy and movement of the particles in the copper during stage X. Stage X, if you will take, you will talk about the energy, high kinetic energy. So if you have high kinetic energy, they will the particles move randomly. Okay, explain why the temperature stays constant and T1 during stage Y. That means why it's here it's constant. As we have said here, the particles, they have high energy. It's right, high kinetic energy because they are liquid. but when you arrive the melting point, this one here, all the kinetic energy it's given out. Okay, so during the Y, all the energy is giving out. Okay, and when it's given out, what it will happen here when it's given out, that means you have you are cooling, so giving out, and you will say cooling. Okay, so you need to say at stage Y, all the kinetic energy it's given out. That means the reaction it's exothermic, because when you will convert it from liquid to solid, that means the physical bond started to be formed. Okay, formation of bond it's exothermic. Okay, and here we have cooling because the temperature is decreased. So you can say it's given out of the temperature, given out of the energy, and cooling. So by the end of this question, we have solved all of these 3 questions. And from the page 9, you will see all the mark scheme are listed here in these pages. And from page 10 to 13, you may check your answer with this mark scheme, and then you will correct yourself as we have learned. And because you know the correcting yourself, it's the best way to score high level. Okay, so thank you for listening and watching this episode, and see you in the next episode. See you.